Imagine a world where things can be in several places at once, where to get somewhere, you can take several paths at the same time. A world where two particles separated by several thousand kilometers could influence each other instantly and where a wall would not be one. Well, that reality already exists, and it is even possible to do all that on an empty stomach. You will have understood. Today, we are going to dive into the strange properties of matter at the infinitely small scale. Focus on the oddities of quantum physics. In this somewhat disjointed episode, I will try to summarize for you, without math and with images, the greatest discoveries we have made about the nature of reality on a microscopic scale. A nature that, as you will see, can be disorienting. The first of these great discoveries is that at the nanometer scale, the behavior of the elements found there is extremely different from those of the world around us that we call classical, because quantum objects such as an electron, a photon, or a neutron can behave both as a wave and as a particle. Take a so-called classical object, for example a phone, and throw it towards a wall with two slits. You will only have one possibility each time you throw. Either it goes through one of them, or it crashes into the wall and bounces back. And each time, if you filmed the experiment, you know exactly where it was and what happened to it. For subatomic particles, things are different even when they're broken. When they move, it has been found that they can take all possible paths at the same time. And it's only when we try to measure where a particle is that it suddenly collapses into a point. In other words, at the nanometer scale of reality, quantum objects can occupy several positions at once, go through several paths at the same time. As shown by this computer simulation of the wave function of a single particle sent towards two slits. We can see that part of this wave is reflected while the other goes through the slits and continues its path. On the other side, what we have represented here is, in a way, all the regions in which the particle that we have thrown towards the two slits can be found before we try to observe it. Thus, at the quantum scale, a particle, something that we are used to representing as having a material consistency, a precise position, must be described in the form of a probability wave of presence. I had already spoken at length in a previous video about one of the most fascinating experiments in physics that allows us to show this. To refresh your ideas, go this way. And if you find what we just talked about strange, wait to see the principle of superposition of states. Let's take our phone back. If you throw it and have fun studying its movement, you can know at any moment how fast it is moving relative to you. I'm stating the obvious here. This object has only one speed in space relative to me, relative to you. But now, imagine that we could reduce ourselves to the scales of an electron. Then all of this would shatter. Because at the quantum level, a particle, and therefore, as we have seen, a wave, can be in several states at once. States that are said to be superimposed. To put it another way, an electron, for example, can be both here and there, have several speeds, several energy levels at the same time. And it's not that we don't know what its state is until we've tried to measure it, it's that it can literally have several at the same time. And when we try to know the value of these superimposed states, then we somehow force the particle to choose among its possibilities. Thus, as strange as it may seem, an electron can be in an excited state and at rest at the same time. And it is only at the time of measurement that this superimposed state will have to decide. Take a position. It's a bit like if you're playing the trumpet in both G and back, but the only note you finally hear only decides at the last moment when it reaches your eardrums. And what is perhaps even crazier about all this is that the result we are going to find, the value of its speed, the place where the particle is going to turn out to be, is partly determined by chance. This chance is not the rotten fruit of ignorance. It is intrinsic to what we observe. It is an integral part of reality at the microscopic scale. A reality that is said to be indeterminate, because there is no way to know in advance where the electron, for example, will manifest itself. What will be the result of the measurement? But beware, this does not mean that the values found can give anything and everything, because this randomness does not decide haphazardly. It is governed by constrained probabilities, in the manner of a dice, as slightly rigged in advance, highly unstable and possessing faces much smaller than others, forbidden results. If, for example, a particle is in two superimposed states at the same time, that its speed is, say, 1,000 kilometers per second, but also 3,000, well, if you try to know the value, at no time will you fall, for example, on the average of the two, because its speed can intrinsically not be 2,000 kilometers per second. In fact, everything happens as if each time we try to measure the speed of an electron, for example, it pulls out its wave function card telling it what its value is, throws its biased dice, which is more likely to fall here than there, and depending on the result, it appears here or there. This brings us to another very strange aspect of the quantum world, namely that at these scales, things can be quantified. Although the quantum world may seem crazy, not everything is permitted there. It is even in a sense extremely constrained, because some values are inherently impossible to possess. That's why it's said that at this level of reality, things are quantified. That is to say, a wave function can only adopt certain forms or values. That an electron, for example, can only possess speeds, distinct and extremely precise energy levels. A bit like a musical instrument that can intrinsically only vibrate in certain ways, being allowed by its characteristics to play only certain notes, because the intermediaries would be forbidden to it by laws impossible to circumvent, those of nature. In short, quantum physics plunges us into a discontinuous universe. A universe of stair-step values in which particles can only abruptly pass from one waveform, one energy level, one speed to another, with no in-between possible. And we are indeed forced to admit that there is something deeply disturbing. It's a bit like if we could, in our everyday life, only and exclusively use a few volumes and nothing else. As if we could only drink a small glass, an entire bottle, but no intermediate volume. As if it were only possible for us to move at certain speeds, with no possible intermediate. That we could drive at 20 kilometers per hour, but if we started to accelerate, to rev up, nothing would happen. Until all of a sudden, we find ourselves there at 150. This oddity, at the microscopic level, is the norm. And to come back to the example of our superimposed particle, moving at 1,000 and 3,000 kilometers per second at the same time, if you could reproduce the same measurement thousands of times under identical conditions, then you could start to see proportions appear for these energy levels, for these speeds. They could be something like a 50% chance of getting one value or another, like 90-10, 25-75, or anything else. In short, you get the idea. At the quantum level, particles can be in a superposition of states with quantified values. And here, you might be wondering why things at the macroscopic scale obviously don't have these kinds of superposed states, when we are made up of a heap of quantum particles, which, all taken individually, do have this type of behavior. Well, the answer lies precisely in the fact that around us, when we, unlike laboratory conditions, subatomic particles are constantly interacting with each other. Thus, in our environment, as soon as a quantum object is superimposed in two states, it is as if forced by all these continuous interactions to choose in an extremely short period of time which one it has. Mine currently being that of a superposition of incredulous sobriety. This time, called decoherence, which becomes shorter as the object studied is large and bathed in an environment rich in light and matter, makes each state superposition terribly fragile. To give you an idea of the fleetingness of the phenomenon, a complex molecule in the air around us sees this superposition of states disappear in 10-30 seconds. The same molecule in an almost perfect laboratory vacuum, but in the presence of light, will be able to maintain it for 10-13 seconds. And it is thought that in intergalactic vacuum between the stars, it should theoretically be able to keep it for 32,000 years. You find this unsettling? Wait until you discover Heisenberg's uncertainty principle. Let's take our phone again and throw it in the air. If you know its mass and the initial throwing conditions, you should without too much trouble be able to know its falling speed and final position. Even without further analysis, we can say this without being a genius. If you haven't lost sight of it, you even know exactly where it is. In the classical world, every object is in a specific location at any given moment. But for a quantum object, none of this is true. At this scale of reality, It has been discovered that it is literally impossible to know both the position and speed of a particle with precision. And this is true no matter what your measurement tool is. In the quantum world, the nature of a thing at a moment is always partly inherently elusive. To put it another way, if the position or speed of a particle can be perfectly known, it's always at the expense of the other parameter. And the more precise you are about one value, the less you are about the other, and vice versa. Imagining that my phone is quantum, it's a bit like if by studying its throw, I could say, okay, I threw it at 22 kilometers per hour, but I have absolutely no idea in which direction. It could well be just about anywhere around me. Or, by locating it, knowing that it is currently precisely there, I lose all precision on its speed, which could just as well be at the moment I measured its position, from 0 to 1,000,000 kilometers per hour. Heisenberg's uncertainty principle tells us that as our knowledge of one property increases, our ignorance of the other does the same. Condemned to always be a bit in the blur, to see clearly only one aspect of reality at the same time, this uncertainty principle imposes a limit on what it is possible to know at a moment to at nanometric scales. If you precisely locate its position, its speed starts to fluctuate. And conversely, if you know its speed precisely, it's the position that becomes indeterminate from then on. Imagine if in our macroscopic world, when trying to finally measure the position of an object, its speed becomes poorly determined, and vice versa. Ladies and gentlemen, we are currently flying over Paris. But I am quite unable to tell you if our ground speed is 10 times that of sound, or if it's too slow, or if we are currently in free fall. I can now give you our exact speed. We're traveling at 559 miles /h somewhere above Europe. In short, this principle tells us that we can't know everything at once, that we have to make a choice with each measurement about what we want to know. This thing is so weird it gives you a very slight headache. I hardly feel anything. But it's so precise, it's so localized there, and like a gaping hole, it's a ready-made excuse to approach the white hole tunnel effect. Let's take our phone and throw it against the wall again. I'm really sorry. I think we can agree that even if we repeat the experiment hundreds, thousands, billions of times, the result will always be the same. At no point will it cross. But a quantum particle, on the other hand, can sometimes cross seemingly insurmountable obstacles, such as walls, as if an invisible tunnel opened and gave it access to the other side. This big chunk of strangeness draws part of its explanation from the fact that at these scales, particles are also waves. Probability waves that, if they have a lot of energy, will, upon encountering a wall, certainly bounce back for the most part, but also for a tiny portion, penetrate into the wall, see if it's not too thick, and cross it. Like a sound wave produced by your neighbour playing grindcore, and which, upon coming into contact with your crepe paper wall, is able to find itself on the other side. I open a parenthesis. The fact that a tiny part of this probability wave crosses the wall does not necessarily mean that the particle will cross it, but that in its wave function form, it is on both sides of the wall at the same time, and therefore there are numerous possibilities for the particle to appear on the other side of the wall if we try to find out where it is. A bit like if, by miracle, a tiny tunnel had opened. And as strange as it may seem, without the existence of this tunnel effect, these kinds of jumps in space at small scales, we would not be here. Because if, above our heads, the stars are able to shine by merging elements, it's because the electric barrier, seemingly insurmountable, which tends to repel the nuclei of atoms when they get close, can be overcome, thanks to this effect, which allows both entry and exit. It's also this effect that allows us to understand how an atomic nucleus, having become unstable, can disintegrate by emitting high-energy particles. Indeed, to escape from the powerful nuclear force known as strong, which holds together the protons and neutrons of the atomic nucleus, these must be able, when they are extremely agitated, to exceptionally escape from their prison. And again, to escape, to free themselves from the grip of the nucleus, they go through the tunnel effect. This phenomenon is called radioactivity. In fact, by taking advantage of this ability to cross great distances at the nanometric scale, which we also find in electrons, we have been able to develop tunneling microscopes, the principle of which is based on a metallic tip placed in a vacuum and which is brought close enough to atoms whose electrons, thanks to this effect, can exceptionally come to tickle the tip of the microscope. And since the probability of seeing an electron jump towards this tip is extremely low and decreases drastically as we move away from the atom, following a well-known law, then we are able, from the study of these jumps, to reconstruct the surface topography of materials at the nanometric scale to discover where the atoms are and the voids separating them. Undulating and peculiar at the same time, superimposed, quantified, and intrinsically uncertain, so many properties that may seem aberrant and yet are necessary to cross, by the sheer force of thought, what separates us from this reality, which escapes our first intuitions. As strange as it may be, these baffling behaviors of matter at nanometric scales are perfectly described by the theories we have and verified in practice by experience. Quantum is not a figment of the imagination. It is found everywhere, has given us all of today's computing and surely of tomorrow, like delicious migraines. By taking advantage of the strange wave behavior of electrons, we have learned to use them in electron microscopes, as we would with light to illuminate objects, and thus exceed the limits of optical magnification. It's our ability to play with their energy level that allowed us to invent lasers, like LED lamps. There are thousands of examples. As effective as it is in describing reality at small scales, quantum physics remains, by its nature, frustrating, because it leaves you with a sense of incompleteness due to the immense and sometimes impossible task it requires to represent it. And to end this video beautifully, I wanted to talk to you about the fascinating phenomenon of entanglement and these experiments that show that two electrons separated by several thousand kilometers can, like some kind of telepaths, influence each other instantly. Except that after literally spending 2 days turning the problem over in every way, at no point did I manage to capture the magic of the demonstration, to the point of finally giving up. Facing quantum physics is sometimes like standing in front of a monument of efficiency with mysterious contours, not in the sense of the misunderstood, but of a monument built in a crazy landscape, which we guess is splendid and blurry, and which would require to be painted at its true value, to know how to speak the language of its inhabitants, mathematics. But I personally only have words at my disposal as a weapon, which find their limits there, and come crashing down on the immense strangeness of these little things, which I dared to attack without having all the power and abstraction capacity of these mathematical tools. Perhaps the only crutches that allow you to continue moving forward in this landscape when you've gone too far. Perhaps the only way to access phenomena so far removed from our common senses. And by constantly traversing these winding paths without this weapon, stunned by these strange particles that we've encountered, I ended up losing sight of the horizon, getting lost, to the point of seeing the ground of reality that I thought I knew slip away under my feet before ending up crushed by the tiny mass of these subatomic particles whose behavior literally left me knockout. And I tell myself that, all things considered, I quite like, I think, the idea that the final word is ultimately that of a delicious frustration, of a nature that refuses me, and perhaps a little also to you. Sorry. And because you are still here, and that 250 pages are always worth more than a video, I warmly recommend you to read The Canticle Otherwise by the physicist Julian Bobroff, a work to which this video owes a lot. This book is fantastic. Many of the animations I showed you are from the excellent site Julian and his team created to make quantum accessible. It's a superb entry point, and you will find a lot of educational content to go even further in discovering this world.